Well, good afternoon. I appreciate you being here with me today. My name is Edward Winter, and I am Vice President of Remediation Products Incorporated, which is based in Golden, Colorado. I happen to be talking to you from Louisville, Kentucky today, and the topic we're going to talk about is daughter products. So I will give people a little more time. It seems like people are still being added to the call. And I will also make use of you guys by turning on your microphone so someone can tell me whether or not you can hear me, if I'm loud enough, etc. before we get started, since I'm here by myself today. And you are unmuted, I think.
I can hear you.
Ah, that's what I need. Now, how clear am I to you?
You're clear.
Excellent, excellent.
Sound good.
Yep, well, we're still adding people, so we'll get started here. Give them a few more minutes and I'll get going. And thank you, I appreciate your help. Okay, I'm going to get started. We're going to talk about chlorinated ethenes, such as TCE and tetrachloroethylene, and the various transformations that they undergo, producing daughter products. Probably the most famous daughter products are DCE and vinyl chloride. And as many of you on this call know, those particular daughter products are actually more toxic than the parent compound, and that's really the issue. The quality and quantity of the daughter products themselves depends on the specific chemical structure that's being remediated and on other environmental conditions, such as, I'll throw out humates in the aquifer or something like that. For this webinar, we'll present data examining the outcomes from remediations and the daughter products they create. And what I'll stick to for simplicity's sake is PCE, TCE, and beta elimination and reductive dechlorination. There are a lot of other aspects and rabbit trails we could take, but it would just make the presentation a little too complex. So the classic example of an abiotic pathway is zero valent iron. So most of you have heard of that. RPI's BOSS 100 product also uses this same abiotic pathway. So I will compare ZVI and BOSS 100 through that comparison, so you'll be oriented to the abiotic pathway or beta elimination pathway. Now, there are a variety of products on the market that have ZVI or metallic iron as their key component. You can grind the ZVI to different sizes and gain some advantage that way. The smaller the size, the faster the reaction, the more surface area relative to weight. The ZVI can be sulfonated. If you sulfonate the ZVI, you prevent some degree of passivation of that iron particle. In fact, if you look at it under electron microscope, sulfonated ZVI is kind of puffy, where what you see with just straight ZVI is as it oxidizes, it becomes very hard and ceases to be reactive. So you gain something with ZVI, with sulfonated. And it can also be mixed with activated carbon. The idea of mixing ZVI with activated carbon is that as you produce some of these daughters and other products, they'll be absorbed by the activated carbon, so you won't see them so strongly in the monitoring wells. And then over time, as they bleed back off, they'll be degraded. The second degradation approach, which we'll discuss, is enhanced reductive dechlorination. A lot of people just call it ERD. I'll try to say enhanced reductive dechlorination for those of you who are new in the industry and haven't quite got down all the acronyms. This is a biological dechlorination route, and that can be either through a co-metabolic process or a direct process. The classic example of enhanced reductive dechlorination is emulsified vegetable oil. I think that's where most people would be aware of this process. So these are two general approaches to dealing with chlorinated solvents, which we'll discuss. And I will say again, there are other approaches, but these are the main ones. So throughout the presentation, I think we probably loaded up now with people who are going to come. The lines will be muted as they are now, and I'll take questions. Just put them in the chat box, and I'll try to get to as many as I can at the end of the presentation. If you'd like to email me any additional questions or questions I didn't get to, my email address is there on the screen, and it'll also be on the closing screen. And I'd like to thank everybody for being here and giving me a piece of your afternoon. So BOSS 100 uses the abiotic pathway, the dechlorination pathway. So in that sense, it's comparable to ZVI. In another sense, it's not anything like ZVI. And it's in the manufacturing process that makes it unique. The iron is fired into the activated carbon under a nitrogen blanket at 850 degrees C. And because of that, you end up with some unique properties. It addresses a broader range of contaminants than does ZVI. It restrains daughter product production. And again, most abiotic pathways are not going to produce very many daughters, but once you get into the subsurface, you start seeing that you will see those daughters, not just from this pathway, but from competing pathways. But nevertheless, it restrains daughter products. It persists even at pHs above 9. So what you'll find with ZVI is they tend to like the more acidic pHs, but as you go up, the ZVI doesn't like those pHs as well. And I need to make the point with this firing process that BOSS 100 is not just activated carbon in ZVI. It is integrated, so the iron is actually integral to the activated carbon. Because of this firing process, the BOSS 100 becomes a new substance. But nevertheless, it shares some of the abiotic pathways, so we will use that also in our ZVI comparison. Now I have two pictures here. The picture on the left is nanoscale ZVI and activated carbon. And this is probably the very best mixture of ZVI and activated carbon that you can get. And this is where you would ball mill the activated carbon and the iron together. So now I'm going to try something really dangerous, which is to use the pointer. So let me see if I can grab the pointer here, and I might be sorry if I do that, but I'm going to. The white that I am now circling in this picture, that is the ZVI in the activated carbon. The black is the activated carbon. And the lesson that should be taken away from looking at this picture, and let me get rid of the pointer now. That takes a minute. Okay. Let's see, that's always confusing to use that pointer. Nevertheless, so the white is the ZVI, the black is the activated carbon. And what I want you to notice is how little of the activated carbon is actually ZVI. But this is probably, again, the ball milled is probably the best you can get on the market at present. This particular picture is from the journal article, which I cite above. What's on the market may not be exactly like this. I have looked at it in the lab, and I noticed that when you put it in solution, you get a big puff of coloration, which is not consistent with the iron being fully integrated in the carbon. But nevertheless, it probably works reasonably well. Now on the right side is an XRF image, which is an X-ray image of BOS 100. And what you're seeing is the difference between that, which is N, which you see on the left-hand side, which you see on the left-hand side, versus metallic iron, which is actually N, that is structurally part of the BOS 100. And that's the lesson of this particular picture. On versus in. Now, there is a problem with just mixing iron, metallic iron, ZVI, with activated carbon. The electrons or atomic hydrogens must be transferred from the ZVI to your PCE or TCE for reductive dechlorination to occur. The TCE molecules that are absorbed to the activated carbon are protected from that process by being hidden in the activated carbon. The additional problem is that if the iron, the ZVI and the activated carbon are not integrated, that during injection, you know that iron has a greater density than the activated carbon, so the injection process itself can cause additional separation of the iron and the activated carbon. So the electrons or atomic hydrogens now have a barrier to surmount in reaching your TCE, PCE, etc., because the iron is not co-located with the activated carbon. So what you really want is synergy, not competition. You want the iron and the activated carbon to work together. Now, even the ball milled, which I showed you earlier, if you look at a publication by Gao et al. From Oak Ridge Laboratories, they looked at this and they concluded that even with the ball milling, you're not really getting a synergistic effect. So with that, I'm going to throw out, before we get into the deeper aspects here of this presentation, I'm going to throw out a note of caution. Be wary of vendors offering physical mixtures of activated carbon and ZVI. The original patent, and you can look it up there, I've given you the patent number by Robert Gillum, was never commercialized. And there's a good reason for that. It doesn't work. It creates a competition, not a synergy. I shouldn't really say that it doesn't work. Okay, the carbon continues to function as carbon. The ZVI continues to function as ZVI. It's just not a synergy. I think that I probably need to modify that statement a little bit. Now, in contrast to the iron and activated carbon mixture, in BOS 100, the iron and activated carbon are merged. They have a constant and direct contact with one another. There is synergy. In a sense, the iron particles are embedded. They're almost an alloy. So the electrons from the iron can reach TCE throughout the BOS 100. So now let's go into the beta elimination pathway itself. So I have the diagram up in front of you. You can see, you can go from PCE, TCE, DCE, and the blue arrows indicate the direction of the beta elimination pathway. So from PCE to dichloroacetylene, TCE, chloroacetylene, DCE, acetylene, they don't necessarily react or move in the way that I just described them, because you can go from dichloroacetylene to chloroacetylene to acetylene, which is the more direct pathway and the more typical pathway. The value of this abiotic dechlorination and why people like a product like a ZVI or the BOS 100 is this kind of degradation pathway is usually complete. You don't produce many daughters. I will say at least that is true in laboratory studies. You don't get the daughter products. So if you look at the X marks, those are reactions that are not part of beta elimination. So you're not producing vinyl chloride. And I would say you're not producing ethene. That's true as far as the beta elimination goes as a description of that reaction. But hydrogenation will take you to ethene and ethylene, or ethylene, which is a different spelling of the same word, without too much issue. The value of this beta elimination is it's effective over a wide range of concentrations. The main drawback is that with a ZVI, the iron oxides, they will tend to corrode. And when that happens or oxidize, it may prevent further reaction from occurring. As I mentioned earlier, in acidic condition, corrosion byproducts from water may be soluble, so you can keep your ZVI going a little bit longer. But at pHs above, say 9 or 10, all depends on the aquifer characteristics, passivation occurs pretty quickly. Now, the dechlorination reactions themselves are kind of heterogeneous. And because of that, the rate of the reaction will depend on the specific area of the iron present in water. So as we mentioned earlier, a smaller particle, you will get an increased reaction rate. So there's some value in that. On the other hand, with the BOS 100, it's actually in to the carbon and it's not really a particle. So the surface area is very great. Dechlorination of highly chlorinated ethenes will allow some intermediates. In the lab, you won't see them. In the field, you will. You'll see DCE, primarily cis DCE. The TDCE actually reacts a little faster through hydrogenation, so you don't see much of that. So why would you choose the abiotic beta elimination pathway? Beta elimination does not produce significant toxic daughters. In the subsurface, it's rare to have pure beta elimination, as I've mentioned. Nevertheless, it's a good system to keep daughters down. Abiotic dechlorination is usually slower than microbial, but Abiotic dechlorination is usually more complete. You have fewer moving parts. It's a fairly simple system. You get a reasonably certain outcome. And when I say certain outcome, I'm not saying necessarily that you will reach your remedial goals. I don't know that, but it will work. It will do something fairly consistently. It's effective over a wide range of concentrations. The weakness of the beta elimination pathway, at least certainly with ZVI, is longevity. The strength of the BOSS 100 is it has significant longevity, which is not really the topic of this presentation, though I will show you some of that later. Now, this slide is intended to show you the acetylene production by BOSS 100. This is a classic beta elimination signature. A good ZVI reaction would give you a similar signature, though it probably wouldn't last near as long as what you're seeing in front of you. So you see in blue the TCE starting at 20,000 parts per billion at the time of injection. It pretty much crashes, and then you'll see it bounce around a little bit. You see the acetylene, which is the end product of the beta elimination climb. So this is your beta elimination signature. The acetylene to ethylene has two different pathways that can get you there. One of them is abiotic, which is hydrogenation. It happens, usually it's not much of a problem. You don't usually see acetylene build up very much, but just letting you know that there's that abiotic pathway. There's also a biotic pathway where a Paleobacter or Acetobacter will ferment acetylene to ethanol, acetate, and hydrogen. And this can be very useful to you because Dihalocoides macarte like hydrogen. They need to be fed. If you don't feed them, they will not live. So, that can be a useful reaction to you, even though we are right now talking primarily about beta elimination, which is an abiotic reaction. So we have a second product at RPI, which is called CAT 100. And CAT 100 adds the biotic route to this should say BOSS 100. So we add the biotic route to BOSS 100 to get CAT 100. The key elements of CAT 100 is you have activated carbon impregnated with metallic iron. That's the BOSS 100 base we've talked about. We add to that complex carbohydrates, a food grade starch, a set of microorganisms designed to degrade your COC, and say it's TCE, PCE, and a second set of microorganisms that are designed to degrade the carbohydrate, the starch, to monomers. So this combines your reductive dechlorination or your enhanced reductive dechlorination with your beta elimination in one product, in one single technology. The idea behind CAT 100 is to build up a synergy between the abiotic and the biotic, the enhanced reductive dechlorination, and hope that the sum is greater than its parts, which it turned out to be. So CAT 100 will outperform either BOSS 100 or any EDR product alone. It will degrade contaminants that ZVI will not. It'll degrade contaminants that EDR will not. Microbes themselves love activated carbon as a habitat, so you will see the microbial population boom and be sustained. It also appears that the microbes themselves are able to preserve the metallic iron that electrifies the process in beta elimination. And they do this through products of fermentation, such as hydrogen ions and electrons. It's low maintenance, it has extended performance. Now, what is enhanced reductive dechlorination? And this goes beyond, what we're doing with CAT. This is a general definition. Enhanced reductive dechlorination is in situ bioremediation that promotes anaerobic biological dechlorination through direct or co-metabolic processes. You can have biostimulation, where you provide optimal conditions for your microbes, and that's primarily what EDR is. So you can put vegetable oil in the ground, or there you go, that's EDR. You can put starch, that's EDR, and there are just almost a huge list of things that people have tried over the years. You can add to that bioaugmentation by putting microbes in that you think will help the dechlorination reaction in some manner, or you can combine the two together. In the marketplace, all of this is done. So the carbohydrates that we provide are fermented to produce these low molecular weight fatty acids, such as, acetate, lactate, propionate, butyrate, etc., which in turn provide carbon and energy for the anaerobic bioremediation. These fatty acids are metabolized by the microbes to release hydrogen, and this process will deplete the aquifer's dissolved oxygen and other electron acceptors, including nitrates and sulfates, which typically lower the oxidation reduction potential, thereby creating conditions for reductive dechlorination to occur. The electron donor that's used most in dechlorination by microbes is molecular hydrogen. So it's important to produce that. So acetic acid and hydrogen production in the subsurface by fermentation of edible oils, for example, will carry out a similar reaction. Bioaugmentation with CAT, where you add the microbes to break down the starch in the COC, moves you forward. And I should point out, just because I know that probably 90% of the people on this call or more have heard of Dehalocoides species. There's a publication by Flynn et al. In 2000, you just type that into Google Scholar and you'll come up with it, that demonstrated complete dechlorination of PCE to ethene with a mixed culture that did not contain Dehalocoides species. So when you're looking to see whether you're getting your reaction that you hope for, look for more than the presence of Dehalocoides. That's kind of a side note with the EDR reactions. Daughter products. And they just move in, you think you're doing well on your site, and suddenly there you have, vinyl chloride or DCE, and your client is unhappy. They just kind of move in and take over the playground. Now, each step in the reaction that you would be looking for in EDR, your biological degradation, is catalyzed by an enzyme. And the absence of a particular enzyme can produce stall. It's not the only thing that produces stall, but it's an easy way to understand where stall comes from. So a couple things to note from this picture. I've marked PCA, which you can see between PCE and TCE. This represents the gene that produces the enzyme necessary to carry out the reaction that takes you from PCE to TCE. PCA, I should say, also can take you from TCE to DCE, but it cannot take you from DCE to vinyl chloride. And that's why I've put the notations of the gene and the enzyme product above each of these reactions. Now, in the lower part of the reaction, I noted a bunch of microbes that can do this first part of the reaction. That was just to kind of indicate and help you understand that there are more microbes than Dehalocoides, which can carry out at least part of these reactions. The value of Dehalocoides is it contains the enzymes that can carry you all the way through the end from PCE to ethene, as opposed to wondering if you have the right consortium that will take you to the end. So enzymes are specific. They work one by one. This is a kind of picture many of you have seen multiple times, I'm sure. But an enzyme has a very specific three-dimensional shape, which can bind a molecule, such in this case as TCE. And once it binds that molecule, it changes the energy necessary to carry out a reaction. And in this example, you see TCE binding as the enzyme substrate complex, then breaking off and spitting out DCE. Why is this important? Because if you have PCEA can carry out all these reactions, yes, but if you lack a key enzyme, whatever it happens to be, and it will not carry you beyond DCE, what you will see is DCE build up. And that's a key component of where the daughter products come from, is lacking a key component necessary to move you forward. Another aspect is that, let's say you do have those enzymes, but they are not necessarily housed in the same microbe. So then at that point, you kind of have a logistical issue, and that you need to move the DCE to the next microbe. And so for that reason, you can also see buildup. So the lack of a particular enzyme can cause stall. The lack of co-location can cause stall. Now in this particular slide, what I want you to see is the daughter signature of BOSS 100, which you can use this as somewhat as a stand-in for ZVI, even though they are not the same thing. They're using a similar reaction pathway. So we'll compare that to EDR to understand the difference between the two reactions. Notice the axes are on the same scale. Notice the low DCE and VC, vinyl chloride levels for the BOSS 100. They're all less than 10 milligrams a liter. Also notice that the BOSS 100 started at TCE concentration that is 4 times higher than the concentration for the EDR reaction. These samples are from the same site. They're obviously not from the same wells. So, I can't really tell you that this is a perfect comparison. It's the comparison I have. Note that DCE and VCE levels are noticeably higher for EDR, and that the DCE was actually not restrained for 21 months, and that the vinyl chloride is still 115 times MCL at the point of last sample. Now, that doesn't mean that the EDR has in some way failed. This actually embodies the lessons that we've been talking about. The beta elimination pathway, which is being expressed on the left-hand side, the BOSS 100, is producing very low daughters. The EDR pathway, which is prone to produce daughter products, is producing daughter products. So you see the DCE lump. and you see the vinyl chloride sustained. Now, in the upper right-hand corner of each graph, I do give you the percent reductions. So you can see that the TCE percent reduction for the BOSS 100 is 99.9. The TCE reduction for EDR is 99.2. That's pretty good either way. But when you go down to the vinyl chloride and you see that the vinyl chloride reduction for the BOSS 100 is 93.4%, and the vinyl chloride reduction for the EDR process is 2.7%. You see the difference. Now, in this particular case, just so you'll know, this EDR is an emulsified vegetable oil. I don't want to tell product names. That's probably not appropriate. So you can definitely see the difference. Okay, so let's look at this. And what I want to show you now is not a BOSS 100 comparison to EDR, but a CAT 100 comparison to EDR. So here is the TCE concentration for the CAT 100. And you'll see that you're up there at above 10,000 micrograms a liter. I believe that would be 50,000 micrograms a liter actually, right? And you'll see that by day 108, it appears to have been restrained to a level that it's at the reporting limit and doesn't appear on the graph. Now, if you look out later at day 758, 759, and in the day 1000, you will see that it pops up again a little bit here and there. This is to be expected, and you will see that for both products in this graph, because both sites, these are two different sites, have to be fair there, but both sites had significant sorbed mass. So next is the DCE concentration for the CAT 100. And again, it's not making it disappear by any means, but it is restraining that. You have to trust me on that. I don't know what you compare that to, right? But nevertheless. And then the vinyl chloride. So this in front of you is TCE, DCE, and vinyl chloride for CAT 100 on a site with significant sorbed mass. So it's going to be hard to actually beat down all of those products as you keep getting mass bleeding off of the soil from this 50,000 micrograms a liter concentration. I would also point out that the CAT 100 was injected one time. The EDR was injected at the same time in a different area, a different site, but that's where we're putting it on this graph. Now the graph gets a little messy. So here is your EDR TCE concentration. It's only at 1,000 micrograms a liter, and it takes it out to, 613 days to 825 days, something like that, before you've actually restrained the TCE. Again, this site was also dealing with significant sorb mass. Actually, excuse me, this isn't the same site. This data is off the same site. It was only the previous day. It was this data is off the same site. Okay, so there's your TCE. And then here's your DCE concentration. And you'll see that it goes up and is really sustained for a long period of time relative to the CAT. And finally, you see your vinyl chloride. So in this, you see kind of the classic EDR pattern with the EDR material. Again, this one is another emulsified vegetable oil compared to the CAT, which seems to, you're not really sure, but you think, well, maybe it has a kind of a mixed pattern. And also, I should point out for consistency's sake that the EDR was injected twice. So you can see that second injection point for this slide. So the main point was to just notice these patterns and learn from the pattern as you see it. Now I want to focus on CAT 100 and show you the products of both beta elimination and EDR. So I want to be able to pick those two reactions apart within the same product. So this is your trichloroethylene. It goes down rather rapidly, as we've seen. This is your cis DCE. You see that it pops up consistent with the TCE going down and then builds a trend, a downward trend. And here's your vinyl chloride. Now looking at this, you really couldn't tell me right off whether this is a abiotic or a biotic pattern because you are seeing daughters. And okay, so this, which I just popped up, is acetylene. So you'll remember from the earlier slide that beta elimination produces acetylene. So this acetylene tracks the beta elimination. And you can see the beta elimination occurs early. And you'll see it kind of drops off as the TCE drops off, which makes some sense. This is going to become a bowl of spaghetti, so you really have to focus. Okay, this is tough. Oh, and more spaghetti. So this is the ethane. The significant drop there is probably just some sort of collection error or laboratory error or something like that. I doubt that it dropped that sharply and then popped back up, but who knows? Graph the data as you get it, right? So that's your ethane, which you would recall being a product after the ethylene. So here's the ethylene, which I probably should have presented first. So that makes sense. You see the acetylene pop up, you see it drop down, you see the ethylene and the ethane go jump up. Those could be a product of both biotic or abiotic, either one, right? The ethylene and the ethane. Now it becomes even a greater bowl of spaghetti. The brown line I just put up is acetate. That is definitely a product of microbial metabolism. And you'll notice that as the acetate peaks, that's kind of when the acetylene is dropping off. So you see your abiotic being replaced by a biotic process. They're not completely replaced by any means, but you're just judging it from this graph. And if you were just looking at this graph, you would think of it as a replacement. You also produce methane, which is good, and carbon dioxide, both markers of biological degradation. And in this bowl of spaghetti graph, you can kind of see that the CAT 100 product is functioning both through an abiotic and a biotic process. Here's another graph from another site, and there are 3 lessons from this graph of CAT 100 data. Now, I like this graph. This same site has a number of graphs where the TCE just dies. You see very few, if any, daughter products. They're dead right on the spot. But that's not very interesting. That's a boring graph. I'm not really sure what you even learned from something like that. But in this graph, I really like. I like it because you see the struggle. You can see that DCE, the blue line. See the DCE come up, go down, and come up, and go down, and come up, and go down. The same way With the ethylene, you see it start climbing, but it's still up and down. The vinyl chloride is up and down. You know, this is a real struggle. This is a fun graph to look at. It was probably leaving the client a little bit on edge for a while there, but ultimately, you can see that the remediation was successful. You see strong production of ethylene. And I will also point out with this, notice the November 2016 to the October 2018 timeframe. That's really where you tend to be struggling with that DCE, VCE issue. And that'll come up here in just a moment. There is another aspect to this. It's not the main aspect of this webinar, but you should notice this time frame. This is one injection. Actually, there are two injections marked, okay? So what happened is you start the full-scale injection on that heavy black line, and a full-scale injection was completed with the double line. So this is really one injection, and 6 years later, you still see the ethylene production. You're still, the cat product is still functioning. Now the next slide is the same data, and all I'm showing you here is chloride production. The proof of dechlorination is chloride generation. So if you see good, solid, consistent chloride generation, you know that the cat is continuing to work for over 6 years. Now, this is the microbial population from the same data that you've been looking at through this slide, and here. Now, the halocoides has everything you need to take you from PCE to ethene. The halobacter has that PCA that tends to drop you at DCE. TCEA will move you from DCE to vinyl chloride. And in fact, if I punch this one more time, I will bring this up so you can see it. Now, it's a little bit of a problem because it covers up the top of the bars in order to get it into the picture. But this helps you understand what you're seeing as far as the picture goes. So TCEA is taking you from DCE to vinyl chloride. BVCA can take you from DCE all the way to ethene. And VCRA does similar things. Now I'm going to go backwards if I can. Let me see if I can do this. Woohoo. And what I would also want you to notice is the total eubacteria that we've been able to maintain over the period of time that the bacteria was sampled from December of 15 to June of 21. We've been able to maintain that population. Now, earlier I asked you to look at a couple dates. I asked you to look at the date from, I believe it was November of 16 to October, or maybe October of 18. And that's where you see the TCA. It seems to be very weak. It pops up and drops down. And that little pop-up you're seeing there happens to correspond with that struggle with the DCE. Now, whether that actually that's just a visual correlation and I've just made up that the two things have a connection, or whether they actually have a connection, we of course don't know. But it is an interesting observation, because that would be consistent with having to deal with a little extra DCE, though even if you had no TCA at all, this would still work. So the summary, there are two key dechlorination pathways: beta elimination and enhanced reductive dechlorination. Beta elimination is represented by ZVI. Its strength is you get low daughter products. Its weakness is longevity. It just doesn't last long. Enhanced reductive dechlorination is represented by emulsified vegetable oil. Its weakness is daughter products. And how long it lasts? Well, it's fairly cheap. You can just keep injecting it over and over again. So in some sense, you could say it lasts long, but one injection doesn't last very long. And if you're not careful in throwing it in the ground over and over again, you will get some microbial reactions that will, well, leave you chagrined. BOS 100 operates through the beta elimination pathway. The daughter products are low to none. As daughter products are produced, they are absorbed also into the activated carbon, so you don't see as much as you would for, say, ZVI. However, they do share a similar pathway. BOS 100 is not ZVI and activated carbon mixed. That's really important to us. It is metallic iron integrated, impregnated, alloyed with. We've tried to use every word we can think of. It is in the activated carbon. It is not on the activated carbon. It's not nearby the activated carbon. It's not pseudo co-located. It is an integral part of the activated carbon. It's an alloy. It has longevity, as you saw, 6 years out, still going, unmatched by ZVI products. The CAT 100 product adds EDR to the BOS 100. It has more daughter products, but the daughter products are controlled relative to pure EDR. And it also has extended longevity. And I should have added here, you have a much faster reaction rate than you would have with pure beta elimination. Okay, so that's the thanks for attending note, and I sure appreciate you attending. You can email me anytime you like or call. It's not a problem. And let me go to the questions and see what I got. See, hopefully nobody will ask me anything I can't answer. Somebody's got a question that says, see, maybe I don't know how to use this thing. Give me a second. Oh, I do know how to use this. One moment. Okay, what effect does BOS 100 or CAT 100 have on PFAS compounds co-located with chlorinated solvents? Oh my goodness. Okay, this is a pet peeve and a hobby horse or whatever you want to call it. Activated carbon, the way it functions in dynamic equilibrium with a contaminant that it can absorb that's in the dissolved phase. Okay, so let me give you something from hydrocarbons to give you this example. And I apologize for leaving the chlorinated, but it's an easier example. When you inject activated carbon in a hydrocarbon site, the first thing you'll see is benzene crashes. It'll almost go to zero. And then you watch, and guess what? Benzene comes back. And benzene comes back as a lot of the other alkanes, which make up the vast majority of the mass of gasoline, displace benzene off the activated carbon because those alkanes have a higher heat of absorption than does the benzene. But because the benzene is more water soluble, in a sense, beats them to the carbon. But later off, it gets thrown off. Why does something like that happen? Because how tightly a particular chemical can bind to the activated carbon is very particular to that chemical. And the heat of absorption would be one measurement that you could use to understand how a chemical or how tightly a chemical is going to bind to activated carbon. So BOS 100 is activated carbon. Cat 100 is activated carbon. We've talked about the iron being integrated in the Cat 100. That's not pertinent to this question. The PFAS will be absorbed to the activated carbon. However, it's still in equilibrium with the dissolved phase. And like the benzene, anything that comes rolling down the pike that has a higher heat of absorption than PFAS, which is just about everything, will kick the PFAS off the activated carbon. So could you treat a site that had both PFAS and chlorinated compounds with, say, Cat 100? Yes, you could. Would your PFAS numbers in your monitoring wells go down? Yes, they would. Could you count on them staying down forever? No. Our products are marketed as trap and treat. There's not a treatment for the PFAS, so we can trap it for a little while, but eventually, and this is a little controversial, but I told you stepped on a hobby horse for me, okay? If you eventually, what will happen is the PFAS that on that carbon is going to come off. So essentially, this is really bad, but essentially you've just built a hazardous waste landfill without a permit. Because there's no way to make that PFAS stay on that carbon. And you can grind the carbon as fine as you want. You can put it in as big a chunk as you want, and none of that will change the heat of absorption of PFAS compounds. Now, there may be some very small PFAS compounds that it would hold, but those are not usually the ones you're primarily worried about. Let me see if there's another question here. And again, I apologize for going too far there, but it's important. Am I missing questions, or are there other questions? Yeah, make that bigger. Oh, yes, here we go. I'm learning how to use this, folks, so forgive me. I can hear you fine. Have the slides started? I hope they have. Oh my God. Oh, okay, good. I thought my slides weren't moving, so I was reading from the top to the bottom. Okay, let's go with, have you successfully used BOSS or Cat 100 in carbonated bedrock? Yes, we have multiple times. And if you email me, I will send you presentations on that. We had a project where we injected straight microscale ZVI into a bedrock fractures, and it was passivated within 6 months. 6 months is pretty good, actually, for ZVI, presumably due to the formation of iron oxides, iron and calcium carbonates, and precipitants that coated the iron. And yes, that would be a correct and expected outcome. Okay, what effect does BOSS 100 and CAT 100 have on PFAS? So we got that. Next, can you share the slides? Absolutely, they'll be sent to everyone who attended today. Could you discuss options available for getting BOSS and CAT into contact with groundwater? Can you use wells with screens, DPT points, trenching it into cutoff walls, and others? Okay, so kind of another little hobby horse here. Our products are put into ground by, at least when we're doing in situ injection, okay? We do high pressure in situ injection. And we do that for a variety of reasons. With the CAT product, it is a granular activated carbon, so it's too large to go through well screens. So, and you're not going to put something like that in by low flow. It's not going to happen. So we put it in with high pressure. Can you put it in trenching? Yes, we've done a lot of PBRs, which I guess trenching cutoff wall, it's essentially the same thing. And we've done a lot of bedrock injection. fact, it's a specialty of ours, and we have probably a bedrock injection system like none other in the country, at least none other I'm aware of. How effective is BOSS 100 in high velocity aquifers? I think given that it's a granular carbon, it pretty much stays put. But that's such a general answer to a general question. You would really have to talk about very specifically the aquifer itself. But it's rare that you have an aquifer that's moving so quick that you can't, put a granular carbon and have it stay in place. I believe that's all the questions I have. If there are any others, I'll give somebody a minute to type it in. Otherwise, I really appreciate everyone attending the presentation. If there's anything you need from me, give me a call or email me. And again, I appreciate you being here today. Okay, I see no further questions. Enjoy your afternoon, assuming it's afternoon where you are.